Hi everyone, my name is Bernardo, and today I'm going to present you implicit manifold Gaussian process regression. So Gaussian processes are among the most adopted models for learning unknown functions within the Bayesian frameworks, providing at the same time a well-calibrated uncertainty quantification. So a Gaussian process is a distribution over function characterized by a mean function and a covariance function, sometimes called kernel. Regression with a Gaussian process is achieved by calculating the posterior with respect to a set of labels y, and the posterior distribution is another Gaussian process, and we use in this case the mean function to do prediction, while the kernel to do uncertainty quantification. The extension of Gaussian process to manifolds is motivated by the many application areas that nowadays require non-Euclidean priors. And in this project, we are trying to investigate the possibility of improving high-dimensional models by adapting the prior to the implicit low-dimensional manifolds. In order to do that, we need a well-defined kernel of manifolds. We focus on the matern kernel, and in manifold settings, this kernel is expressed as an infinite sum, weighted sum of functions. Here in blue, you see the smoothness parameters nu and the dimension of the manifolds that are fixed, while in red we have the signal variance sigma and the length scale of the kernel that are the hyperparameters that we want to optimize. Lambda L and FL are the eigenvalues and the eigenfunction of the Laplace-Beltrami operator that encodes the geometry of the manifold. So consider this one-dimensional H-shaped manifold, for example, where the gradient represents the function that we want to learn. We observe the functions at only few locations onto the manifold. And in this project, we focus on the scenario where not even the knowledge of the manifold is available, and we would like to infer it from data. So first, consider the possibility of having many unlabeled points. And we proceed by constructing the adjacency matrix based on a symmetric k-nearest neighbors graph, where the graph bandwidth alpha is an additional hyperparameters that we want to optimize for. We then proceed by applying an intermediate renormalization to the adjacency matrix by the degree matrix before constructing the random walk normalized version of the Laplacian. And we do this because this procedure ensures point-wise convergence to the Laplace-Beltrami operator independently from the sampling distribution. We build this operator in a matrix-free and completely differentiable way, and thanks to the KNN graph, this operator is also sparse. In order to optimize the hyperparameters of our models, we propose to maximize the marginal likelihood expressed via the precision matrix. In our context, the matter precision matrix can be constructed starting from the random walk normalized Laplacian. And thanks to the particular structure of this precision matrix, we can actually express the derivatives of the quadratic term in the marginal likelihood as a sequence of matrix vector products without ever having to construct explicitly the precision matrix. The other term derivatives can be kind of calculating, leveraging the same structure through conjugate gradient. In the semi-supervised scenario, we compute the labeled portion of the precision matrix through the Schur complement. And for noisy observation, we build the noisy precision matrix through Taylor expansions. In this way, we have a scenario that where we have a matrix-free, sparse, and fully differentiable problem. Once we optimize the hyperparameters of our model here in green, we rebuild the kernel, leveraging on the eigenvalues and a KNN-Nystrom extension of the eigenvectors of the random walk normalized Laplacian. And here you can see the behavior of the reconstructed kernel that exhibits the kernel geodesic decay proper of the underlying manifold structures. The resulting model is built as a combination of the geometric Gaussian process posterior and the standard Euclidean one modulated by a bump function gamma. And by looking at the posterior mean, we can notice how leveraging on the knowledge of the manifold, our methods guesses correctly the value of the function in the central portion, while far away from the manifold, our models converge to the prediction of the Euclidean models. In the same way, for the uncertainty quantification, in the central part where the manifold geometry matters, our model kind of corrects the overconfident behavior of the Euclidean models and again, away from the manifold, posterior standard deviation converged to the Euclidean modus 1. Thanks to the sparse structure that we have in our algorithms, we can scale up to high-dimensional settings. This means high-dimensional both in feature space and number of samples. We tested it on rotating MNIST and on CD slices dataset from the UCI machine learning repository. And by looking at specifically the semi-supervised case scenario, we can see how the knowledge of the manifold sensibly boosts the performance in the negative log likelihood matrix, suggesting that our model can help in not only improving prediction, but also uncertainty quantification in high-dimensional settings. Thank you.